Okay, so let's get started. So this is Physics 3011 Classical Mechanics 1. Okay, so I'm Dr. Marco Lai. I'm the lecturer of this course. So here I will just go through the course outline quickly. And here you can see my contact information, my office location, and my consultation hour. Okay, so some of you might not be available during this consultation hour. Maybe you have other classes, but you're always welcome to try to find me in my office at other times. Okay, so so for me, because the other course that I'm teaching this semester is Physics 1712. So that you know that one is a laboratory course. So that means that for Monday to Wednesday, I will have to be staying in the teaching lab for the whole afternoon, basically. So for those days, you might not be able to find me. However, you can still try to go to 213 to look for me. Okay, so if I am free, I can still talk to you over there. Okay. Okay, so I guess I've seen most of you in the last semester in the class 2051. So although I don't think I recognize many of you because many of you don't come to classes. Okay, so I don't know because maybe because it's a Zoom thing or something like that. But so here, so this semester, okay, you can see that I'm still doing the Zoom recordings, but I haven't decided whether I will just put everything on Blackboard. Okay, so I'll just keep them. Okay, so if someone has special reasons that you cannot come to the campus, then I'll definitely give you the recording. But otherwise, I think I need to think about whether I'll just put everything on Blackboard. Okay, to be decided. Anyway, so first let me introduce our TAs. Okay, so Mr. Meng Chenqi. So he was also the TA of the same course last year. Okay, so he did a very good job, and so it's good to have him again for the course. So here you can see again his contact information. Okay, so you can find him in his office for the whole afternoon on Friday, right? According to what he said. Okay. So and then next, Mr. Dang Yato. Okay, so again, he is also he was also a TA in last year for the same course. Very glad to have him again for us. And then again here you can see his contact information. Okay. So finally, Mr. Zhang, okay, he has other commitments, so he cannot come here today. But since the first year he be the TA of this class, so treat him nice. Okay, so and here is his contact information. Okay, so as you understand, so the 3 TAs will be responsible for the exercise classes and grading your homework and the midterm exam, right? So so there's for the exercise classes, you can see the schedule over here. Okay, so this year there will be a slight different arrangement from last year. Is that in order to make things more time more efficient. So what I'm going to do is that for a particular week for the exercise class, okay, so one TA will take care of all the sessions. Okay, so for example, okay, first of all, there will be no exercise classes this week. Okay, so the first exercise class will be on next week. Okay, so for example, for the next week, so Mr. Tang will take care of all 3 sessions of the exercise classes. Okay, and then the week after, okay, so the other TA will take care of all 3 sessions of the exercise classes, and then just basically do the rotation. Okay. So this way, I believe then the TA can just focus on the material of a particular week, and then okay, so that then better preparation can be done. Okay, okay, up to this point, I think that you two can go. Okay. Thank you. Right, so lecture class and tutorial class. So during the tutorial class, if you have taken 2051 last semester, you might notice that during the tutorial class, I might give some exercise problems or some tutorial problems that for you to work on during class. Okay, so in this course, I might also do a little bit of that, but maybe not as much. Okay, because I need more time to go through the lecture notes. Okay. Okay, so here are the textbooks and reference books information. Okay, so just same as last year. Okay. So assessment scheme, you can see that 23% go to homework, 32% go to midterm test, and then 45% go to the final exam. Okay. So any question up to this point? Okay, so if not, let me quickly give you an idea on what you'll learn in this class, right? So I believe that for most of you, right, so this is not the first classical mechanics course that you had, right? So in the last year, I believe that you had either the physics 1111 or the physics 1113, right? So then, what are the new things that we are going to learn, right? So because from the last class, I believe that you have used Newton's second law, right? So to deal with many different kind of problems, right? Maybe circular motion, simple harmonic motions, gravitations, and so forth. Right? So, but in any cases, you are just basically start with the Newton's second law, right? So find all the forces and then solve for the equation. So what are the new things in this course, right? So I would say that there will be 2 main things that should be new to you, right? So the first one is that instead of starting from the Newton's second law, right? So basically in the previous course, you just treat this Newton's second law as some sort of a fundamental principle, right? So and then you start from there. Okay. So here we are going to start from another principle. Okay, so which we call the principle of least action. Okay, so and then we treat the principle of least action as the starting point, and then we go to obtain the equation of motion. Okay, so and the equation of motion that we will obtain, okay, mathematically it turns out that it will have to be, well, it will be exactly the same as what you would got from Newton's second law. Right, so that means once you get the equation of motion, which are exactly the same, and then the later steps are just mathematics, right? So then, but the key idea is that here we set up the equation of motions in a different way, okay, starting from a different point, right? So I can just really give you a very quick description here is that, so I believe that you have learned about this motion under constant gravity, right? So suppose I have a ball here, and then you just throw it up vertically, right? So this is the whole region is under a uniform gravitational field, G, right? So what happens is that the ball will rise, and then to some point it will fall back down, right, to the same ground, let's say. Right. So if you plot a graph of the position, let's say this position x versus t, right? So then you'll be able to draw a curve like this, right? So it moves, and then it slow down, and then stop, and then fall back down, and then as it falls back down, the speed get higher and higher again. Right? So this is what you got from this Newton's second law, right? So now using the least action principle that we'll learn, okay, so that we think about this problem differently. So is that suppose, right? So we basically know that the particles start from this point, okay. So and then end at this point, okay. So suppose we have these 2 points known already. Right? So and then let's draw different curves, okay. So although okay, we know that this is the one that is actually happening, right? So but let's draw other curves that are actually wrong, okay. So for example, this one, the red one, we know that this is not the correct path, right? So because if it is the case, and that means that the particle will just go up at a constant velocity, right? So and then just go back down at another constant velocity. This is wrong. That you know that, right? So and you also know that, right? The path won't look like this, right? So the red path and the blue path are just wrong, right? They don't obey Newton's second law. Right? So what we'll learn, okay, with the least action principle is that suppose, okay, so we allow ourselves to consider different paths, okay, so and pretend that we don't know which one are correct, right? So just I mean, just pretend that we don't know Newton's second law. I guess that's one thing, okay, but you are allowed to draw many different paths of many different shapes that connect these 2 points, right? And now for each path, what we are going to do is to calculate a physical quantity, which is known as the action. Okay. So the action is defined by the time integral of a quantity, which is known as a Lagrangian. Okay. So of course the time goes from let's say at this point the t is 0, right? So and at this point t is tf. So from 0 to tf. Okay. So for each path that you can draw, right? So you can find out the time integral of this. Okay. So but what is this Lagrangian? Okay. Let me save this later. Okay, I'll tell you. But suppose you just all you need to know at this point is that given a point and a velocity, you can calculate this a quantity which is known as the Lagrangian. Okay, so this Lagrangian is a function of position and the velocity of that particle at a particular time. So then you could imagine that although we don't know how to calculate it at this moment, right? So but because at this point, right, so they have different value of L right? So, and then you do the integral, basically you're summing up all the time point, the L for all the time points, right? So, and suppose, right, so for the blue curve, you calculate this action S, and then for the red curve, you calculate the action S. You will find that the value of the action for the two curves will be different. Okay, so and then among that many possibilities, you'll find that the black one actually gives you the least value of the action. Okay. And that is the correct path. Okay. And it turns out that that path is also the path that obeys Newton's second law. Okay. Okay, so this is the big picture, okay, of the thing that you learn. Okay, so this is this kind of formulation, right? So in classical mechanics, we call this the Lagrangian mechanics. Okay, and then the other closely related formulation is known as the Hamiltonian mechanics, which you also learn in this course. Okay. So this is the main new concept that you all learn in this course. Okay, and it turns out that the idea of this least action principle, like this Lagrangian and Hamiltonian formulations, okay, they don't just appear in classical mechanics. Okay, that's the beauty of these formulations. Okay, if you go to more advanced topics, more advanced subjects in physics, okay, so you see this kind of formulation again. Okay, so concept-wise, this is the new thing. Okay, so. And the other thing that so that should be new is that you'll be dealing with more complicated problems and systems. Okay, so for example, in your year one, I'm sure that you have learned about oscillators, right? So mass spring system, right? So this is something you have learned. Okay. So here we'll also talk about oscillator again, but this time more complicated is that we have multiple springs and mass. Okay, so we call this the a coupled oscillator. Okay. So and also I believe that you have learned about gravitation, right? So in your first year, right? So the F equals minus the mm divided by r squared, right? So you have let's say you have a sun here, and then the Earth orbiting around, right? So it's but I believe you might not have learned the exact how to obtain the exact shape of the trajectory, right? So in this gravitation problem, right? So in here, right? So we'll mathematically, right? So derive, show you that the few different possible shapes of the trajectories of this planet, right? So under this gravitational field. Okay. So the simplest case is the circle, and then you might also heard of that in most situations is actually an ellipse, right? So and in fact, it can also be a parabola or hyperbola. Okay. Okay, so and then one more thing that is new is that you'll be dealing with the so-called non-inertial frame. Okay, so when we solve for this mechanics problem, right? So we usually just consider the observer to be either at rest or it is moving at some constant velocity, right? So, but in this case, we'll show you that in some situations it's more convenient to actually use a reference frame that is accelerating. Okay, so it's either in the linear acceleration, or actually it could also be a so-called a rotating frame. Okay, so basically, here summarizes what I just talked about. Okay, so and one more thing. Okay, it depends on whether we have enough time. Okay, so is that so what I just talked about just now, still dealing with this so-called the point particle, right? So and I believe in your first year you also learn about the rotation of an extensive object, right? So that's the moment of inertia and the things like that. Okay. So here, if we have time, we'll also have a chapter on that. Okay. So what's new here? Okay. So in your first year course, I believe that the rotation that you are talking about is basically an object which is always spinning or rotating about a fixed axis, right? So, but if you have played with a spinning top before, you might know what a precession motion is. Right? Is that the spinning top is spinning, but then after a while, you may see that the axis of the spinning top is doing a motion like this. Okay, so this kind of motion is known as a precession. Okay, so that means we have to deal with a case where the angular momentum of the system is not just that we don't just need to care about the magnitude of the angular momentum, but also the direction. So the direction of the angular momentum is also changing. Okay, and only in that kind of problem, okay, we can really kind of appreciate the vector formulation of angular momentum, right? So I believe that you have learned the definition of angular momentum, right? So R cross P, L equals R cross P is the angular momentum, right? And it is a vector. Okay, but in the case where the rotation axis is fixed, okay, it seems that you might not be able to really get why do I need a vector to represent angular momentum, right? So because it's either spinning anti-clockwise or clockwise, right? So why do I need a vector in 3D space? Okay. So when we have time to talk about these kind of problems, then that's you'll see. Okay. Okay, so some more topics I'll review. Okay, if needed. Okay, so these are the things that I assume that you have learned, right? So for this coordinate system vector and matrices, this is things that you have learned in 2051, and also, of course, differential equations. And actually, one more thing that you need to be familiar with is about defining the eigenvalues and eigenvectors. Okay, and so for the lecture notes, assignments, and other, and all the course materials, okay, will be delivered or collected on Blackboard. Okay, I almost forgot about this. Okay, I will upload this again, this academic honesty statement. I will upload it on the Blackboard, and then remember to just sign it and upload it on Blackboard. Okay, any questions for the course outline? Okay, if not, okay, so then let's get started on the first chapter. Okay. All right, so just now I told you that we need to minimize some quantity, right? It's to minimize the so-called the action, right? And because of that, right? So the first chapter, first I will need to give you an introduction on a mathematical tool that for us to do the minimization. Okay, so and that is known as the calculus of variation. Okay, so you see how it is different from the calculus that you have learned, right? So when I talk about minimization or finding the minimum value, right? So you have heard of that in when you learn differentiation, right? So you have a function and then you want to find the minimum value, you just take the first derivative, right? So and set it to 0, right? So that's the idea. So here we are to find the minimum, we are also taking some sort of derivatives, right? So, but the trouble here is that the input that we have for the function is not a number, okay? So what I mean is that when you deal with a function, right? So you input a number to a function, and then the function output another number for you, right? So input a number, output another number. Right? But here, the difference is that as I show you here, right? So we are going to minimize the action S, but what is our input? Our input is not a number anymore, right? So is that our input is actually a curve, right? So we input a curve of any shape, and then the output after you take the integral is a number. So that means when I say I input a curve, what I really mean to say is that I'm inputting a function. So I'm inputting a function to this integral, right? And then this integral itself will give me a number. So it's no longer like we input a number, get out a number. This time is that we input a function and then we get out a number. And then we want to know what kind of function we need in order to give us the minimized number. Right? Okay, so we'll start with two very classic problems. Okay, so to illustrate the idea of this minimization. Okay, so the first one is known as the path of quickest descent. Okay, or the brachistochrone. Okay, so the second is known as the shape of a slope fin. Okay, so let's get started. Okay, so the first one, let me consider a very simple situation. Right, so I'm sure that you know how to do it. So is that I have an inclined plane. Okay. So, and let's say I have a particle up here. So let me draw it first. So the inclined angle is theta. Okay. So and then the whole thing is just under the influence of gravity. Okay. All right. So now it will just slide down, right? And then eventually it will arrive here. Okay. So I'm not varying any parameters, right? So this is the setup. It's a fixed setup that I give you. Okay. Initially, I should not have this arrow here. Okay. Initially, the velocity is 0. Okay. You just put it there and then you release it. So let it fall down, let it slide down. Okay. So and the simple question I want to ask is just how long does it take for the particle to go from this point to this point? Okay. So that actually should be simple enough for you as long as I give you all the length and the initial condition, right? So let me just simply draw a coordinate system. Okay. So my coordinate axis is like this. So at this point, I call this O, and then the end point, I call this A. Okay. And then at the starting point, my coordinate is just 0, 0. Okay. And then at the endpoint A, I'll just call the coordinates to be x1, y1. Okay. So, and then that means, right? So the vertical distance that the particle has fallen, right? So over this journey is x1. Right? So this is easy to solve because, okay, first of all, we know that the acceleration along this path is a constant, right? So when it is like at this point or at any point, right? So I'm just going to indicate the component of the acceleration, right? So along this plane, which is g sine theta. Okay. So now I'm just going to use, if v equals u plus at. Okay, so I want the t, right? I want to know the time taken for the particle to go from O to A. And the A is just g sine theta. And I just need to know u and v. Right? So u is the initial velocity, which is 0, and then v is the velocity at this point. Okay. So let me just write v equals to u, which is 0. And A is g sine theta. What t? Let me just call this TOA. Okay, so then I just need to find out v, right? So v is again, it's easy to find, right? So v, you just need to, if you just use conservation of energy, right? So 1/2 mv squared would be equal to m times g times what? Times this distance. This distance, as I told you already, is x1, right? So then v is just square root of 2gx, right? 2gx1. So then this TOA, the time taken to travel from O to A, is v divided by g sine theta, which is square root of 2gx1 divided by g sine theta, right? So I want to express the sine theta also in terms of x1 and y1, then basically what I have is this. Right. So just that. So now, what I'm going to consider is a more complicated path. Okay, is that what I just have is this just a straight inclined plane from O to A, and then suppose at this point I join it with another plane. Okay, so from A to another point. Okay, so just like this picture now. So what I just consider is the situation from O to A. Right. So, and then now the second section of the path is from A to P. Okay. So now I have a parameter that I want to vary. Okay, that is the position of this intermediate point. Okay, so the starting point O and the ending point P are fixed. Okay, and then okay, so the vertical level of this intermediate plane is also fixed. But suppose I am free to choose the horizontal position of this A. So that is, I can either pick this A or this A prime, or the other point over here, A double prime, and so on, right? So let's say, for example, this is the A double prime. If I pick the A double prime, then the path that I would have is like this, right? So there are infinitely many choices, right, in principle. And now I want to ask, okay, so which path should I choose if I want to take the least time from O to P? Okay. So you can see that if I, for example, if I take this path A, right, so I will first have this section with this length, and then the second section is this one. Right? So how does it compare with this A prime path? Right? So that if I pick the A prime path, right, so in the first section I will have a shorter distance. Okay, so but then in the second section I'll have a longer distance to do. Right? So this is the first step of the first problem that I want to introduce. Okay, but of course it is not the actual problem that we need to consider yet, but I would like to start from here. So this one is actually not difficult to do, right? So just with the knowledge that you already have, right? So because what you need to do is that you need to calculate the time taken from O to A, and then also calculate the time taken from A to P, right? So and you just add the two together, then you know the total time. So here, right? So I'm just doing the math here, right? So for this first line here is something that you have already seen, right? So this first line here is exactly what I have over here, right? So and then for the second section, right? So from the A to P, right? So if you go ahead to use the same set of equation of motion, right? So this is what you will get. Okay. So the slightly more complicated formula here is just because, right? So if you calculate the time from A to P, right? So the initial velocity A that you have here is no longer zero, right? So for the first section, right? So the initial velocity is zero, but when it go to here, then it's no longer zero. So that's why the formula is slightly more complicated. But regardless, right? So it's manageable, right? So you have now TOA and this TAP. Okay. And also what you can see is that both of this TOA and this TAP can be treated as a function of y1. Okay. So what is y1? Okay, remind you again. Y1, right, is the horizontal coordinate of this A, right? So remember, we are free to choose the horizontal position of A. Right? So that's why this y1 is exactly the parameter that we want to vary. Okay. So now, total time, right, just can be obtained by adding up this and this. Right? So, but anyway, those two are just function of y1, right? So you just get a function of y1, and then remember the x1, xf, and yf are all fixed, right? So they are not variable. So then now, if you want to minimize, right? So find the minimal time, then you just need to take the derivative right? So you take the d capital T d y1, right? So that's what you're going to do, and then you will be able to find the corresponding value of y1 and the corresponding value of t. Okay. So I'm not actually going to do that over here because this is actually not the problem that we want to solve. Right? Okay, so but what we're going to consider next is that if I further make it more complex, that instead of 2 segments, okay, so this time I have 3. Okay, you understand the same idea, right? So this time, right? So I have 2 parameters that I can change. Okay, first is this point A1. Okay, I'm free to move this point A1 anywhere along this line. Okay, and then the A2 also free to move this point anywhere along this plane. So this time we have 2 variables and they are independent. Okay, 2 independent variables that we can vary, right? Y1 and Y2. Okay, if I pick Y1 over here, right? So I'm free to choose any Y2 the other way. Okay. So they don't need to be correlated. Okay. So now, right? So again, I'm asking what kind of what Y1 and Y2 I need to choose if I want to minimize the time that the particle takes from O to P, right? So this time, if you go ahead and write down the expression for the total time taken, you see that this is a function of 2 variables, right? So Y1 and Y2. So, and a function of 2 variables, right? So you find the minimum, right? So I believe you also know how to do it, but you just need to take the partial derivative, right? So you need to take the partial derivative, and to set the partial derivative with respect to both variables to be simultaneously 0. Find the corresponding Y1 and Y2. Again, this is not actually the problem we want to solve, though I'm not going to do the math here. Okay, so you might see where I'm trying to go is that think of more and more layers, right? So until you basically get infinitely many layers. So, and then you could imagine that in that case, you no longer get a path that looks like segments of straight line. Instead, you get more like a curve, right? So maybe a curve like this, right? So maybe a curve like this. Okay. So this is actually the problem that we want to deal with. Okay, so now I have O and P. Again, the starting point and ending point are fixed. I no longer tell you, okay, so I'm going to make a segment here and over there. Here I basically allow you to choose any curve, any path that you can choose, okay, that you want to draw, right? So I'm drawing 3 of them here, right? So there are infinitely many of them. And then the problem is that the question is the same, is that I want to find the path which gives me the minimum time. Okay, so that's the problem that we are going to solve after the break. Okay, so here, so let me see the promotion from the Physics Society. So we'll take a break for 15 minutes. Okay. Okay, so let's continue. All right, so basically we are at the point of getting into solving the actual problem that we want to solve, right? So I have an arbitrary curve, and then I consider the time taken for the particle to go from the O to P. So first, let's find out the expression, right? So for the time. Okay. So in this case, right, you could imagine that the acceleration, right? So it's no longer a constant, right? So if you just have an inclined plane, then your acceleration is also always g sine theta, right? So but here, because of the slope at different points are different, so the g sine theta at different points will be different. So but still, okay, so luckily what we can do is that by conservation of energy, right? So we will still be able to find out the v at different points, right? So even without knowing the details of the acceleration, right? So suppose the distance that it has fallen at this point is x, right? So then we know that again just by conservation of energy, right? So the v is given by square root of 2gx, right? So no matter what kind of shape that you have, right? So for a particular level x, then the v is given by square root of 2gx, right? So here let's consider a tiny segment of the curve, right? So I'm just going to consider this tiny segment over here. So I'm going to call the length of this to be ds, okay? And then the vertical separation over here is dx, and then the horizontal separation right here is dy. So the time taken for the particle to go from here to here, I'll call this dt, okay? And this is equals to ds divided by v, okay? So the v at this point, okay? So as this, because again the same argument, right? So because the segment is infinitesimally small, then within this segment, then the v is just a constant figure. Okay. So and so let me just write 1 over v times ds, and what is ds, right? So ds is actually square root of dx squared plus dy squared, and it is further rewritten as this. Okay. So now 1 over v, okay, we got it from here. So it's given by 1 divided by square root 2gx. So now I want the total time. right? So the dt. So total time, of course, is the integral of dt, and that would be the integral of this function here. And the x endpoints are known, right? So the x position and the, of course, the y position of the endpoints are all known. So x go from 0 to, and then the to xf. Okay. So that means we are going to minimize, we want to minimize this integral. Okay. And now the information or the shape of the function, the shape of the curve, right? So we'll give you dy dx. Right? So this dy dx, right, really depends on the shape of your curve, right? So then you can see how this time, right? So it really depends on what shape of curve that you pick, right? So because you need to give the information of this dy dx. Okay. Okay, so this is just repeating what I've just written down, right? So minimizing this function over here. So again, I'm just going to repeat what I said half an hour ago, right? So in calculus that you have learned, right? So when you find the minimum of a function, right? So the function that we are talking about is that the function will take one number as the input, and then it output another number. So that's a function that you were trying to minimize, right? And here, this is the function, right? So and the input that it takes is not a number, right? Instead, is a function. You need to give me the y of x, right? So for all value of x within this range, right? So and then plug it in, and then this gives you a time. So and this is so-called a function node. Okay. Okay. Function node is a function that takes another function as an input. Okay. So we are looking for the minimum of a function node. Okay, instead of that's a function. Okay, so before we actually try to find out the minimum. Okay, so let's get some exercise over here. Is that suppose I give you a curve already. Okay, so I'm not trying to mess with many different shape of curve. I give you a particular shape of the curve, and then I want you to find out the time. Okay, so what do we how do we do it? Okay, so the curve that I'm going to give you, okay, in this example, is the arc of a quarter circle. So this is a quarter circle, okay? And in fact, Galileo Galilei did consider this problem, and he thought that this gives the minimum time. Okay. So although he was wrong, actually, this is not the final answer that we will get for the minimum time, but you'll see what the correct answer is. But at least this is historically, okay, this is what Galileo thought about. Okay. Is that with this shape, right, instead of just a straight line. Okay. So okay, so let's do this little exercise over here. Right, so what I need to do, so I want to, if I want to find out the time, right, so for this integral, so I need to express everything in this integrand in terms of x, right? So that's how I can do the integrate dx, right? So that is, I want to take care of this y prime. Okay. So how do I take care of this y prime? Then of course first I need to see the function of this, right? So because this is a quarter circle, as I told you, right? So and the basically the full circle will look something like this, right? So then this would be a circle that centered at this point, okay, centered at 0, 1, and then the radius is just 1, right? So the full circle, right? So the equation for this full circle is basically so x squared plus y minus 1 square equals 1, right? So but we just need this part, right? This quarter part here, right? So but here if I want to express a y in terms of x, right? So then what I have here is y minus 1 square equals 1 minus x squared, right? And then y minus 1 is equals to 1 minus x squared plus or minus, right? So but if we take this half, it is minus. So that is y equals 1 minus x squared. And that means y prime, you do it, then it would be this. Okay. So now I got the y prime. Okay, so I just need to plug this expression of x to the integrand, right? So then the whole integrand just depends on x, right? So just integrate a function of x. Okay, so I haven't actually tried to see whether this can be done analytically, but you can try. Okay. So but anyway, this is, as I said, this is not the correct solution, right? So but this, in fact, at least is a quicker path, okay, compared to just a straight line. Okay. So, but still, this is not the correct answer. So now we still haven't talked about how to solve the problem. Okay, so but I'll talk about it after I also introduce the second problem. Okay, and then we will see the formulation and then solve these two problems all at once. Okay. So the second problem that I want to talk about is the so-called a slope beam problem. Okay. So you might have played with slope beam before, when you are a child, but the most common type you have seen may be just a sphere, right? So when you in the playground, if you see the children, maybe they just blow it and then they just have all this slope beam sphere. So, and why is it a spherical shape? Okay. And in fact, it is the shape that minimizes the surface area of the film. Okay. So what I mean is that if you have a particular volume, okay, so if you want to given a fixed volume, okay, inside a closed surface. Okay. So what is the minimum surface? Okay, so that can enclose this region of fixed volume. Okay, so that would be a sphere. So, but here, okay, we are consider something slightly different. Is that so? This kind of slope beam, you can see how it is formed. Is that we have two rings, okay, two circular rings, okay, one above the other, okay, and then the slope beam formed between the two wings. So of course this is not a sphere, but the common feature is that in this case, okay, the SOAP film is also trying to minimize the surface area. Okay. So SOAP film always want to try to minimize its own surface area. Okay. So due to the surface tension. Okay. So then I want to know the shape of this SOAP film. Okay. So in this picture, you can see that it really is not a cylindrical shape. It's not like a cylindrical shape with a fixed radius. It looks more like there's a curve, right? So and there's a waist in the middle. Okay. So then, okay, so mathematically, so if we want to try to model this problem, so I just set up this coordinate system over here, right? So and then I draw two rings. Okay. So and I actually allow the two wings to have different radii. Okay. So they have to be concentric. Okay. So both of them lie on the ZX plane. Okay. But they can have different radii. Okay. In this special case, they have the same radii. So now you'll see that in this case, again, we are trying to minimize some sort of an integral. So because of the cylindrical symmetry, okay, so what we can consider is that any shape that you want, right, so can be obtained by first, right, so consider a curve that start at a point P and the other point and at the other point O, and then do a revolution. Right. So, for example, right, in this case, if the shape of the curve is like this, right? So after you do the revolution, right? So then the shape of the SOAP film looks like this. So another example, right? So if you try to, let's see if I can. If you try to draw a curve like this, right? So if you do a revolution, then at the end, right? So the whole surface looks like this, right? So you can construct any surface you want, right? So you just basically you just need to make a curve. Okay, so and then do a revolution. So, but anyway, let me just go back to the grade one. Okay. So how do I find out the total surface area of the SOAP film? Okay. So I'm just going to consider, okay, a narrow stripe first, right? So this narrow stripe. And the surface area, how do I find it? Okay, so all you need to do is to find out the radius times. So why do you need to find the radius? Because after you find the radius, you find the circumference of this stripe, and then times the width of the stripe. Right, so here I write 2 pi r times ds. So where is ds? So ds is right. So I have it here already. So this is ds. Okay. And then this ds can be written as, right? So again, square root of dx squared plus dy squared. Okay. So let me try to. So this is the ds, right? So and then this width over here, dx. And then this width over here is dy. Okay. And then again, it can be written as square root of 1 plus y prime square times dx. Okay. And here the 2 pi r, I can simply write the 2 pi x, right, because of the cylindrical symmetry. Okay, so this x referring to this distance over here. Okay. So now the entire area, right? So you just need to do the integral. Okay. So again, you can see that we are trying to minimize something, right? So and then it's minimizing an integral, right? So and then the integral, the input of an integral again is not just one number, right? So it's a function, it's a curve, right? So this time the curve that you need to give is this curve. So this is a functional. Okay, so now let's get to the method of how to find out the minimum of functional. So from the previous two examples, so mathematically, basically, we are basically considering an integral like this. Okay, so I call this J, and then this is an integral of a function. Okay, the function will contain y prime and x, right? So if you go back to, for example, this one, right? So it depends on y prime and x. In some other problem, it will also contain y itself. Okay, but that's not this one. So and here, right? So also can see that this is a function that contains y prime and x. Again, as I said, in some other problem, it will also contain y itself. But in general, I'll just say that this is the integrand, right? We express as in terms of y prime, and x. Okay. So the first thing that we'll do is that suppose, okay, so we know that, okay, we suppose we know that there's a minimum. Okay, we know that it exists. That's what I'm saying, but we don't know what it is. Okay, so but I'm just going to call the function that gives us the minimum value of J to be y min. Okay, I don't really know what y min is. We just basically assume that yes, we know that it exists. Okay. So and suppose, right? So this y min of x has this shape. Okay. Again, it's just an arbitrary drawing. Okay, it does not have to be look like this. But this is black line. This black curve is this y min x. Okay. So now we consider the so-called neighboring path. So the neighboring paths, just graphically, you can see that, for example, this red one, right? So the one that is close to the y min is the so-called neighboring path. Okay. So or it can be this one, okay, and just anything you can draw. Okay. Now I just basically assume that, or basically say that the neighboring paths, okay, so can be written as this y min of x plus this term. Okay, this one is important. Is alpha times eta of x. So alpha is a parameter that you can change, and then eta is another function. Okay, again, we don't know what this function is. Okay. But this function just has to satisfy the so-called boundary condition that at xi, the first endpoint, the eta has to be 0. Okay. And then also at the other endpoint, xf, the eta has also to be 0. Because the two endpoints, okay, so you cannot alter the value of the two endpoints, right? So then now I will say that the neighboring path, right? So the neighboring path, as I said, is that can be written as the sum of these two terms. And also, if I take the derivative, right? So the derivative of the neighboring path can be treated as the derivative of this y mean plus alpha times the derivative of this eta. Okay. So as I said, we don't know what this eta is, and you can also imagine that we actually have infinitely many choice of eta. Okay. So for example, I try to draw another picture over here. That let's say this is my y mean. And then if the eta that I have is like this, right? Like a sine curve. If this is the eta that I have, then if I want to draw this y mean plus alpha times eta, what will it look like? You could imagine that it will look something like this, right? So this would be y mean plus alpha eta. And alpha is a parameter, right? So if you tune the value of alpha, well, let's say you have this alpha, for example, if I say for this case, alpha is 0.1, so it looks like this. If alpha is minus 0.1, then how does it look? It will look something like this, right? And if you change alpha to 0.5, then how does it look? It might look something like this. Right. So now this is the case. If I draw the eta like this, then the neighboring path all looks like this. Right. So, but you could imagine that if the shape of the eta change, then all the neighboring paths will also change. Okay. So that is right. So that there are really infinitely many choices of eta, right? So, but the lucky thing is that we don't really need to explicitly consider all the infinite many cases individually. It's because if y mean is the true minimum, right? So no matter what kind of eta that you have, right? So whenever you give me a non-zero alpha parameter, right? So your integral will move a little bit away from the minimum value anyway. Okay. So therefore, okay, so we just need to focus on the alpha parameter. Okay. The infinitely many choices are still here. It's all hidden in the eta. Okay. But we don't need to really worry about that if we just really consider the minimum. So therefore, okay, so this integral j, okay, so it was a function of y prime, and x, right? And now I can consider that this y and y prime, okay, they're still function of x, but they are also function of alpha. So therefore, now I just need to take the derivative of this integral j, okay, with respect to alpha. So this is very nice because now we are actually just doing the regular differentiation that we all know how to do, right? So if we actually do it, right, so all we need to do is to well, take this derivative sign inside the integral, right? So and then we just apply the chain rule that you have learned in the last semester, right? So let me write it more explicitly. So this f of y, so y is actually now we consider this one as a function of alpha and x, right? And then this y prime is also a function of alpha and x, okay? And then a function of x. Okay, so this really means this. Okay. So look at this, and then if you apply the chain rule, right, so that you can take the derivative with respect to alpha. Okay, so this is the term that you have, right? So and now this dy d alpha and this dy prime d alpha are exactly the eta x and the eta prime x that we have defined in the last slide. Okay. So now the next step is also a very key step, is that if you look at, so now this is an integral that has two terms, right? So you can do the integral of the two individual terms separately, right? So here I'm just going to consider the integral of the second term, okay? So which is this one. And the integral of the second term can be actually written like this, like this chain rule, okay? And then the trick is that we can do integration by part, okay? So the integration here is nothing but integration by part. Okay. And the nice thing here is that the first term, so after you do integration by part, you get the two terms, right? But the first term will actually vanish, right? So because by definition, the eta of x at the two endpoints have to be 0. Okay, so that's why this term goes away, and then all you have is the second term over here. So now, the nice thing is that the first term comes with this eta x. Now, the second term also comes with the same eta x. So now that you can see there's a common factor, eta x, right? So this dj d alpha, okay, now can be written as the integral of this big term here times this common factor, eta x, right? So then, now the key is that eta of x is an arbitrary function, right? So as I told you already, right? So infinitely many choices that you can make. Okay. And because of that, right? So since we are looking for the zeros of this dj d alpha, and because this eta of x can be arbitrary, so therefore to make this integral 0, okay, so the only choice that we have is this big term here to be 0. Okay. And now this is a differential equation, right? So this is differential equations, and it really contains the relationship information between the y and x, right? Right. So once you solve this differential equation, then you obtain a relation, okay, between y and x, right? So y as a function of x, right? So you obtain this. Now this function y of x that satisfy this equation here will be the one that gives you the minimum value of the J integral. Okay. So this is the key equation that we'll use. This is known as the Euler's equation. Okay. So even at this point, you might need more time to digest all the derivation process, but at the very least, try to accept this result. Okay. So this is the equation that we'll be using a lot. Okay. So it won't hurt you if you forget about the derivation in the exam, right? So but this is what you have to use in the homework in the exam. Okay. So now let's go back to see how we use this Euler equation to solve the two problems, right? So the brachistochrone problem and the slope thin problem. Right? So remember the brachistochrone problem, right? So this is the integral that we had set up already. Right? So don't recognize this. Go back to the slide that you had before. Right? So this is the one that we want to solve, right? So for the minimum time. Right? So in this case, right? So this integrand, right? So is our function f. Okay. Now I want to use this Euler's equation, right? So therefore, I need to take the derivatives, take all these derivatives with respect to this y prime and this x. Okay. So we take this partial f partial y. Okay, we'll find this. This is 0, right? So because this one does not contain y. So here might be something that to be careful is that. So this is the function that I give you, right? So it depends on y prime, right? So but the y prime, of course, will depend on y. Then here, why do I say that partial f partial y is 0? Okay, so this is something that you might be careful. It is because it is how we use the chain rule. Okay, this is how we use the chain rule. So in this step over here, right? So when I apply the chain rule for this function, right, with respect to alpha, right? So even though this one y and y prime, they are actually not independent variable, but when I use the chain rule, right? So you basically pretend, right? So all these three terms are, all these three variables are independent. Right? That's how you do the chain rule. Right? So therefore, right? So when I tell you to find partial f partial y, right? So what it really means is that you are going to assume that x and this y prime to be constant, right? So when I say that I want you to find this partial f partial y prime, okay, what it really means is this. Okay. So with that, this partial f partial y is 0. Okay. And then this partial f partial y prime, okay, you have a y prime here. Right, so then you have this term over here. So now I have this, and then I just plug it back to this Euler's equation. Okay. And this is the differential equation that I will get, right, from the Euler's equation. Okay. So solving this, we obtain a relation between y and x, and that would be the curve that we want, right? So to give the minimum time. So it turns out that this is not that difficult to solve, right? So the derivative of this whole thing to be 0. So that means the whole thing inside has to be a constant, right? So this whole thing is a constant. And then just rearranging terms, right? So you will be able to find that this y prime is equals to this expression in terms of x. Okay. So notice that c is a constant that needs to be determined. So how do we determine the c? Okay. Well, you know that whenever we have solved this differential equation, we always have some constant, right? So then the constant will be given by some initial condition. So, or in this case, the boundary condition. Okay. So, and here I define a new symbol here. So the c is a constant, and then I define 2a equals 1 divided by c. So a is just still a known constant. Okay, so y prime equals to this whole thing here, and that means y is the integral of this. Okay. So this, okay, looks a bit difficult to do, but it turns out that if we do this substitution, we are able to do this. Okay, so if we substitute x equals a times 1 minus cosine theta, then this dx is a sine theta d theta, right? So then what is this one? Then this 2ax minus x squared would be 2a times a 1 minus cosine theta minus x squared. So x squared is a squared 1 minus cosine theta squared. And this is nothing but if you expand all the terms and then you find that sometimes you cancel, and then at the end, okay, this one, you'll find that this is a squared sine squared theta. Okay. And therefore, x times dx divided by square root of 2ax minus x squared would be equals to, right? So 2ax minus x squared is a squared sine squared theta, right? So 1 divided by the square root of this is just 1 divided by a sine theta. And then this x dx, right, it's just a 1 minus cosine theta. And then this dx is times a sine theta d theta. And nice thing is that this a sine theta cancel this a sine theta. Okay. So therefore, this integral is just this. Okay, this is straightforward to do. Right, so then this y equals to this a theta minus sine theta plus some constant. Okay. So these constants, right? So we can take care of, right? So using the boundary condition, as I said, because you. Okay, so let me tell you the final answer first. So this y equals this a theta minus sine theta. Okay. And this theta is somehow related to x, like this. Right. So in the end, okay, so I'm going to present this y, the relation between y and x as this parametric form. Okay. So this is actually known as a cyclone. Okay. So this a value can be found by using the boundary condition. Right? You need to make sure that this cyclone that you have has to pass through the two endpoints. So what is a cyclone? Okay, so a cyclone. So you know what is a circle, what is an ellipse, but how does it look like a cyclone? Okay, let me just show you a picture and we'll just end here. I think they have a nice animation in Wikipedia. Okay, you can see how the red curve is the cyclone. Okay, you can see how it formed. So suppose you have a wheel rolling on the ground, okay, rolling without slipping. And then at a particular point, at the edge of the wheel, you put a marker. So the black point. So and then the trajectory that traced out by this marker point, okay, will be this red curve. And this red curve is known as a cyclone. But actually in our case, okay, so this, I want the cyclone to be inverted. Okay, so it's more like this one. Okay, to imagine that this is an upside down world. Okay, so the cyclone looks like this. So then brachistochrome, right? So the brachistochrome is that you could imagine that if I have a starting point here and an ending point here, right? So then the minimum time path, right? So will be the curve like this. So part of a cycle. And you need to properly adjust this A parameter such that your cyclone can pass through these 2 points. Okay. Okay, so that's we have solved the first problem. Okay, so I will stop here for today. Right, so next time we'll just quickly talk about the slope beam problem. It will be easy because now you know Euler's equation already. Okay, and then it will continue next time.